Hey, what's up everyone? Sam here from This Week in Machine Learning and AI. This video is the recording of our January meetup, our first of 2018. After a lively community discussion in which we discuss various predictions and outlooks for 2018, our main speaker, Timnit Gebru of Microsoft Research, joined us to discuss her paper, Using Deep Learning and Google Street View to Estimate the Demographic Makeup of Neighborhoods Across the United States. I really like this paper and Timnit's presentation of it because it does a really good job of providing an end-to-end view into a large-scale machine learning project, including the many challenges that need to be overcome and the compromises that need to be made. I think you'll really enjoy it. As a reminder, we hold meetups monthly where we cover classic and hot papers in machine learning and artificial intelligence, and we'd love for you to join us. If you enjoyed this video, head on over to TWiMLAI.com/meetup to sign up. And don't forget to like this video and hit that subscribe button.
All right, so we'll get started here. Just a few minutes of intro, and we'll actually jump right back into the discussion, but welcome everybody. This is the 5th meetup, and I'm super excited to start the new year with all of you learning about machine learning and AI stuff. And we'll actually talk about like what our learning goals and all that stuff are in a minute. We are still solidifying our presentation lineup for the year. Some of you, I don't have like the list of names or anything, so I won't put you on the spot, but some of you said, sure, I'm willing to present a paper. It doesn't have to be a paper that you authored. We are fortunate this time around to have the author of the paper that'll be presented, but that doesn't necessarily need to be the case. It just needs to be a paper that you think folks will be interested in, that you're interested in. We do have a Slack channel. I think this little bullet point is a bit of a vestige. When we first started, I tried to kind of push all the conversation to the Slack channel, but it didn't work out all that well. There's also a Zoom chat. There's a Slack channel, whichever works for you. And then Timnit, as she's going through her presentation, will ask for questions from time to time, or if you have a question at any point, just type it in the Zoom or the Slack channel. It's kind of difficult for the speaker to keep an eye on all of those channels and present, so I'll be kind of a proxy for you in asking your questions. But by all means, if you've got a question and you'd like to voice your, speak your question, let us know, or unmute yourself and ask your question. And so, as is the tradition for the meetup, we'll start with a bit more discussion, and I've got some prompt questions here. It's a little bit similar to the December meetup. December meetup, we were talking about like what were the big developments of the past year, and this time we'll be talking about what are your machine learning and AI resolutions? These could be, or predictions, so these could be things that you want to learn. These could be things that you think we'll see. And if nothing else, there are these backup questions. What were your favorite podcast shows of the year? What guests would you like to hear from? And so at this point, I would like to open it up to whoever's got something to share.
Thanks, Sam. Can you hear me?
Yes.
Yes, Sam, thank you very much. I am Mahesh from India.
Hi, Mahesh.
Yeah, hi. And it's a pleasure watching your podcast, and I look forward to a great 2018. In terms of the predictions, I attended an NVIDIA workshop in Mumbai last month.
Okay.
And I had a chance to meet the director of AI of a very large of a company called Ola Cabs. Ola Cabs is a competitor to Uber in India.
Okay.
And they were talking about multi-agent reinforcement learning as a great trend for 2018.
Have we figured out single agent reinforcement learning?
Yeah. It's a great learning time for everybody, I guess.
Yeah. So we talked about RL quite a bit in the December meetup as an area to keep an eye on 2018, and that's definitely something that I'll be both watching closely and hoping planning to learn more about. So it's interesting that you're already starting to hear about multi-agent RL. Did they provide any specifics or point you to any papers or research?
I'll try and share a paper. I'll try and share what I had made notes of that. But what my understanding was that most companies have AI in different line of business systems. What they are wanting to do is in 2018 try and integrate these multiple AI systems into some kind of a holistic approach. So yeah.
I think someone should mute. There is one person who I'm hearing a lot of noise from. I'm not sure who. Oh, okay, it's quiet now.
Oh, that was it.
Yeah.
I've been doing behind the scenes. I'm playing audio whack-a-mole and muting people's lines. That doesn't mean we don't want to hear from you. It means that I think there might be some background noise there, but that's great. So multi-agent, we'll see more of multi-agent RL in 2018. Any resolutions? Did anyone kind of enter the year saying I'm definitely going to take on project X or learn thing Y in 2018?
I think there is so much happening every hour as we speak that whatever resolutions you make are really going to be, you're going to be behind the curve.
Yeah.
It's going to be tough for all of us to keep up.
I agree. Anyone else want to chime in?
Yeah, I have another question for everybody. I also am interested in reinforcement learning in particular, but I come to computer science in general actually from the philosophy department in my school. And I was wondering if anybody else has sort of non-CS, non-computational reasonings for liking a particular subject within AI overall.
So if anyone wants to chime in on that, definitely do. But my first thought was to refer you to the recent podcast I did with, let me look up the name so I don't get it wrong. But this was with Matthew Crosby, and this was one of the shows actually that I recorded at NIPS, and it's on the philosophy of intelligence. And he comes to AI from a philosophy background.
I would say that there's a very high need right now in AI for people who come from very different backgrounds to go into the field, in my opinion, because there are things like, the AI Now Institute, for example, or DeepMind is starting to have this ethics board, and we're starting to have a lot of discussions about the societal impacts of artificial intelligence and things like this. And it's really important to engage with people who don't just come from this one particular straight-laced background. I always have very heated discussions with people who come from one specific background, because they don't they haven't read certain texts, or they haven't seen the world from a particular angle. So I think it's really important to have people like you in the field. And like actually not even just people from, so I work with Kate Crawford, who comes from a social science background. I mean, she's her whole thing is studying, AI from the effects of technology. But her background is in social science, and there's a whole bunch of other people, like even Zach Lipton talked about, he's going to be a professor now at CMU, but he talked about the fact that he was a jazz musician for a few years before he decided to get a PhD in machine learning. So it's really important, I think, to have people from like these different lives and different perspectives getting engaged in the field.
Yeah, and I think
Michael, my background is in economics and policy, and I'm kind of wrestling with how deeply technical I want to get. I'm taking a couple of intro courses here and there. I kind of feel I'm as conversant as as a non-expert can be. But if anyone has suggestions on how to school up without becoming a coder, I've done a little bit of coding, but it's not really my thing.
Mm-hmm.
Yeah, that's an interesting question. I would say listen to This Week in Machine Learning and AI. But I think, one of the things that I think is interesting in this discussion is when we think, I think when a lot of us think about AI, we think about it from the computer perspective, but there are a pretty broad set of perspectives. Like just from the interviews I did at NIPS, there was one of the interviews came from a kind of neuropsychology perspective. The other came from a philosophy perspective. There's AI as it's being applied to the arts. I think my advice would be to identify like the kind of what the intersection of interests are, and try to find various communities that are at that intersection. And I think that I find it hard to believe that you can find or that you wouldn't be able to find, any community around any kind of set of interests that overlap with AI. Like there's so much interest in it right now, whether it's art or law or accounting or what have you. I think that you'll find communities that are working on the application of AI to that specific thing.
Yeah, I definitely agree. I feel like there's a lot of miscommunication about the impacts that AI is going to have on society as a whole, where you have other computer science technologies that don't necessarily pertain to people at large, where something like AI really is, as you were saying, Sam, is just going to affect so many diverse fields, something like, you mentioned accounting or, law, fields that aren't inherently technical, but will still have a huge impact. And I feel like there's just a lot of, miscommunication between what the public at large knows about AI and its impacts versus, the group of people here on in this meetup that, at least have some understanding of what AI is going to do and just a little bit about it. And I think that that's really important. And I think, and I guess I hope that going into 2018 and beyond that, I guess people in general become more aware of how AI is going to impact their specific field. And also, I guess, to future-proof yourself too, just because a lot of, fields will become, I don't want to say obsolete, but, fields will definitely change, and just staying up to date with how AI might impact your field, I feel like is important.
But I think this paper is pretty interesting. You had a lot of people sort of weigh in from a lot of different fields, right? That whether it was CS or not. And to answer Sam's original question too, Berkeley just published a paper titled "Berkeley View of the State of AI." It's kind of a good primer if you're not that. I guess not a technical person, but even if you're a technical person, it's pretty good. And listen to Sam's podcast, right?
Well, if you have a link to that paper handy,
I'm putting it in right now. Yeah,
you can
there's an
drop.
archive
Oh,
link.
nice.
I put it in the Zoom chat, and I'll
Okay.
email it to you too, Sam.
All right.
One of those that all the researchers will cite for research dollars, you know, so it'll be cited by times. Very
good. Very good. So it's a quarter after the hour, and Ben mentioned the paper, so that's a great segue to hand the baton over to Timnit. I will stop sharing, and let's see, did it revert back to yours? I think it did.
Okay, I don't know. I can't tell.
It did. If you
can
go
you
in
guys
slide share mode,
you guys can see my screen?
Yeah.
Yeah.
So if I like enlarge it, like right now, you guys can see my screen?
Yep.
Yeah.
Okay, great.
Yeah.
I'll just start playing from start then. So
it's a little bit like
what's going on? It's cropped.
Yeah, I think it is. Yeah.
Is it? All right. Like, how about like let's just do this? Is this okay?
Was it just me that had it cropped, or
it was cropped, but it wasn't cropping off any content for me. It was just black bars, at least.
Okay, me. Maybe try it one more time.
Okay. And
okay,
so,
yeah.
Is this still cropped?
No, it's not. I think I might have had it zoomed in or something.
Okay. So I'll just start, and if you have any questions, feel free to interrupt in the middle, because I can't see like the chats or whatever because it's full screen. So I'll talk today about this paper. Actually, it's a series of papers. It's 3 papers in total. So a project that resulted in 3 papers culminating in like this PNAS paper we just published. And it's about predicting demographics using 50 million images. So I'll talk to you a little bit about our motivation. So we know the US Census spends at least $1 billion per year trying to figure out demographics, figure out who their constituents are, you know, racial makeup, income, etc. And we also know, on the other hand, there's a lot of pollsters trying to figure out who's going to win the next election. Last year, they kind of got it wrong. But anyways, they try to do this, try to predict who's going to win the election before it actually happens. There are people trying to figure out how to reduce crime in neighborhoods and even like so for example, there was an example in San Francisco where they got rid of parking spots in some area, and they said that reduced the amount of crime there. I don't know if it's true or not. But anyway, so our whole point was, when we started this project, was, can we do any of this using computer vision? And at the time, a lot of people did data mining using text. So that's a very common, and that's a much older thing to do, to use social network data, to use textual data, and to gain some sort of insight from that data, or Twitter, or like Facebook data, stuff like this. And people hadn't really done it with computer vision. So there was this one paper though from MIT Media Lab. It's Nikhil Naik is actually the one of the guys who did it. And so what they did was, this was from 2013. They gathered a data set of Google Street View images, and what they did was they would show crowd workers 2 pictures of 2 different places, and they would say which place looks safer, which place looks more unique, which place looks more wealthy, or things like that. And then they would annotate each image they had with the answers to these questions. Does this make sense? I can't see if people. Okay, I'm assuming yes. And so, okay, cool. So then they now have a data set annotated of images that are geotagged by location, that are annotated with people's perceptions of what this place looks like based on its image. And then what they did was subsequently, them and a couple other computer vision groups they basically trained a classifier using this data set to classify whether a place was, you know, safe, unique, or wealthy, just by looking at its images. And then there was also this work from Berkeley, from Alyosha's lab. And they called I think they called the project City Forensics. And what they did was they looked at basically patches. They also looked at Google Street View images, but so they tried to relate like patches of images to various characteristics. So they found, for example, that like, you know, they found interesting things like if you have, you know, if you're in expensive neighborhoods, then you tend to have like high rooftops or things like this. But all of these, oh, and then there's one more. I think this is the most famous probably example, which is this is from the Stanford AI lab as well, my colleagues. So Neil Jean is the student, the lead student, and Stefano is the lead professor. They used satellite imagery to predict poverty rates. So here you can, I don't know if you can kind of see, but like you can see actual versus predicted values of, what is this? Yeah, like actual versus predicted values of income for African countries. You know, they're okay. There are values are like, you know, R squared values are like between 0.37 and 0.55. So anyway, so the thing about all of these works is they basically use global image features. So what do I mean by this? So if you use pre-trained CNN features, so if you like have a CNN that was pre-trained on ImageNet or something, and then you like input a whole bunch of images, and then you take the feature representation of those images through the CNN, that's like global image features, right? Or if you use, you know, HOG or GIST or SIFT, these are also handcrafted features that we used to use before deep learning. These are features that capture the global characteristic of a particular image. So we were thinking, okay, how can we do this in a better way? So we thought, okay, so if you look at a city, you look at the objects in a city, they tell you, they help you understand what's its constituents, right? So here you see, okay, like there's billboards, there are a lot of people, you know, there's like a whole bunch of yellow cabs, and I know this is New York, USA. And so we decided, okay, you know, we're like a city's objects tell us a lot about its constituents. So we're going to use object recognition in order to understand cities using their images. And the other thing we know is that when you look at, so here I'm showing you the top 5 error rates for the ImageNet challenge. So the ImageNet challenge used to be run by people in our lab at Stanford. Well, I'm not at Stanford anymore, but like in the computer vision lab at Stanford. And every year it's basically, I'm assuming most people know about it, but basically every year a whole bunch of groups compete to get the highest accuracy on a few very basic computer vision tasks. So object detection, which is basically trying to figure out whether there's a particular object in an image or not, and also localize where that object is. So that's object detection. And an object recognition, which is just determining whether a particular object is in an image or not, and you don't have to localize where exactly it is. And segmentation. So we see that you see the top 5 error rate, which means like out of the top 5 things that you predict that this image contains, is one of them actually in the image. So that's the top 5 error rate. So you see that the top 5 error rate has been going down, and now it's you know, the data set is retired, the challenge is retired, because these algorithms are doing like better than people just in this specific, you know, very specific constrained environment. So we were like, okay, we can, object recognition is doing very well. We can use objects to understand cities. So we should just do this. And like, if we're gonna do this, there are two questions. First is, what is our source of data? And second is, what objects do we use? So our source of data, we said, okay, we're gonna use Google Street View images because almost every single address in the US has an associated Google Street View image with it. The second thing we said is, what objects are we gonna use? We're gonna use cars, because cars are, in my opinion, like the most dynamic way, the most dynamic objects that are visible on the outside in Google Street View images that can tell you something about a particular neighborhood. Like, right, so if I told you that I drove a Toyota Prius, you probably have some sort of stereotypes about where I'm from and like, what my political affiliation is, et cetera, et cetera. So we decided we're going to gather 50 million Google Street View images from 200 of the most populated cities in the US, and we're gonna detect and classify all the cars in these images, and then we're going to use the characteristics that we know about these cars to try to infer something about the demographics of the people who live in these cities. Now, okay, so now I've told you, okay, like, object recognition with images is almost solved. Like, we're gonna use objects, blah, blah, blah. So then you might ask, okay, then why is this a computer vision problem? Like, this seems like a solved problem, it seems kind of an easy project. Why did it take you like 3-4 years to do this? And the answer is that mostly getting training data is really hard. So the subset of computer vision that you use to basically where the task is to distinguish between different kinds of cars, it's called fine-grained image recognition. So it's different from like other types of object recognition. In other types of object recognition, I am going to, like, my task is to, if I'm going to label data, my task would be to distinguish between a tree and a house or a person and a car or something like that. Whereas here, your task is to distinguish between very, very similar objects like bird species or cars, right? So, so this is what you want to train your algorithm to do. And in order for you to train your algorithm to do this, you first have to have a data set of images that are labeled with all of these different objects that you're trying to distinguish between. So in our case, we need to have a whole bunch of images labeled with the types of cars they contain. And that is a really, really hard task because in fine-grained image recognition, for example, here, I'm showing you, like different kinds of birds. So not everybody can tell you the difference between bird species type A, bird species type B, but bird experts can tell you. And getting bird experts is really hard, and it's very expensive to pay bird experts to label your data. Now you can imagine the number of objects in the world, and this kind of thing kind of like completely explodes. And then we have, but even within the fine-grained system, when you're talking about birds versus cars, you still have a different problem, because with birds, if I tell you the name of a one bird and then the name of another bird, you know that they look different, because the way the taxonomy works is that the birds with different taxonomy look different, right? They're different species. Whereas cars, it's not the same, because car manufacturers don't always change the look of the car from year to year. So a 2006 Toyota Prius can look the same as a 2007 Toyota Prius. And it could look the same or different, I don't know. It could look the same or different as a car with a different trim, etc. So actually, before we even started to gather training data, we had to assemble a class list of cars. So here you see 5 types of cars. And so like the cars in red, for example, all of these are like, I think all of these are like 2006 or 2007 Toyota Prius or something like this. Now, you know that the cars in red should be in the same class. The cars in blue or purplish should be in the same class, and then the cars in green should be in the same class. Because you look at the car in green, you look at, can you see my mouse? Can people see my mouse? Yeah, okay, so you can look here, right? Like it's very different. I mean, not very different. I'm highly trained, so because, you know, I spent my whole grad school career like looking at cars. But yeah, but you know, you can see the difference here. So the first thing we had to do is assemble, we took down all the cars that we know, let's say 15,000 cars or whatever from edmunds.com. And we're like, oh, we have to get a class list that groups all of the different cars into different classes. Because you can only train a computer vision algorithm to recognize the outside of the car, and I'm not going to be able to tell the difference between a 2005 Honda Accord and a 2006 Honda Accord if those two look the same on the outside. So I have to be able to say, okay, class 1 consists of these, you know, different cars. Class 2 consists of these different cars. So the way we did this is, this is an HCI, this was an HCI paper. So we wanted to, so remember, you know, you have a budget when you're, you know, unless, you know, you're Google or something, I don't know. You know, we had a budget to that, we wanted to spend about $35,000. That was our budget to collect data. And so you have to figure out how to efficiently collect data and with, you know, with the budget that you have. And so that was our task here. So what we wanted to do is we wanted to minimize the use of experts because experts are expensive. And so we wanted to be able to have people in crowd workers be able to do this grouping task for us. So what we did is, so here you look at, I'm representing like different kinds of cars. So we start out with all these different cars, like you say, you know, you have your like 2006, you know, might be year 1. And you have all sorts of cars in 2006, and you have all sorts of cars in 2007. And you know that, you know, cars from a particular make, like Honda, look different from cars from a, you know, Toyota. So here are all cars from, like, let's say Honda. So, and each of these colors represents a node in a graph. And so now I ask people this question. So we show them example images of 2 cars, and we say, are these 2 cars, do they look the same or different? And of course we have instructions to tell them what it means to be the same, what it means to be different. So if they say yes, then we add an edge between these 2 cars. So if red and orange, we ask them, are these 2 cars the same? If they say yes, we add an edge. If they don't say yes, we don't add an edge. So we do this over and over again. And now we know also if red and orange are the same, and red and orange and green are the same, also, you know, red and green should be the same as well. So this sort of, so this should be a clique. That's what we would call a clique. So if, you know, people say red and orange are the same, and they say orange and green are the same, and then they don't say, you know, red and green are the same, then you know there's something wrong, so you redo this particular query. So that gives you a little bit of like a quality assurance sort of thing. So anyway, we keep on doing this, and then
Can I chime in with a question or two?
Yeah, sure.
So in the previous figure with the cars, are these examples of cars that are supposed to be the same, or is it like much finer distinctions that you're looking for, and are
I think these are
different?
I think these are the same. Wait. No. Oh God, I'm so confused. No, these are the same. Yeah, these are the same. Yeah.
Because I remember looking at this this figure and was like, I mean, with the different angles, who knows if they're the same or different?
Yeah. So you know, you have
BMW 3 Series or whatever this is.
So you have next images and previous images, right? So you can see more images.
Okay. And
right?
the next and previous are all supposed to be of the same car?
Yes, of the same. So car 1 has a whole bunch of images, next and previous. That will be of just car 1. And car 2 will be a whole bunch of images of car 2, next and previous. Right? So we're hoping that you'll have enough examples to tell. But if you can't tell, then you have to say like, you should tell us you can't tell, you know?
Okay. So you're comparing 1 and 2, not the 3 images.
No. Yeah, we're comparing 1 and 2.
And then the other question I had was like this methodology, is this the first methodology that you came up with and you ran with it and it worked out, or did you try different things and kind of iterate on the methodology itself?
Yeah, no. This is not the first thing we tried. I mean, we tried a whole bunch of so by the time we did this, it was like the 3rd month, I think. So we first just tried to, I don't even remember what we tried. I looked at a whole bunch of stuff, and then we just tried to we just tried to crowdsource it with no graph-based thing or whatever.
Just like what kind of car is this or something like that?
Yeah. We didn't, and also you have to iterate on the UI as well. So even once you come up with a task, there'll be something confusing about the UI, or people get confused. People don't know how to answer this question. It was still very hard for people to do this task. Or how you're going to do quality assurance, things like this. So yeah, it's never the case where you just, it's rarely the case where you just come up with this thing and this is the first thing that works, right?
Yeah. Does anyone else have any questions before we jump back in? Okay.
I think we're good. Okay, so this is that. And so we continue to cluster cars in this way, and then we finally use connected components, which is like a graph clustering method, to come up with our final list of cars. So now, we have our list of cars. So all we have so far, remember, we still haven't gathered a data set of images labeled with the types of cars they contain. So all we're trying to do right now, we're still not there yet, right? All we know right now is we're class 1 contains car 1, car 2, car 3, car 4, and class 2 contains car 5, car 6, car 7, car 8. So in class 1 has a list of visually indistinguishable cars, and class 2 has a list of visually indistinguishable cars. That's all we know so far. So now we want to gather labeled training data for each of these classes, right? Car 1, car 2, car 3, car 4. So one insight here is, remember I told you what makes fine-grained image recognition hard is getting training data, because you need to have experts. So what we thought was, well, we're not car experts, but I know my own car very well. So when I try to sell you my car, when I go on e-commerce site, then I'm gonna give you a lot of information about my car, and it's gonna be accurate because I'm trying to sell you my car. So that was the insight. And so we said, okay, we're just gonna go on Craigslist and cars.com, and we're gonna scrape a whole bunch of cars. And query cars like 2007 Toyota Prius LX, whatever, or with the trim, with the type of car we want. And then we had to do a whole bunch of other processing with, with Amazon Mechanical Turk. But really, compared to everything else we had to do, we got a whole bunch of labeled images almost for free. Not exactly, but almost for free.
And so were you specifically doing query by car type as kind of the initiation? And then, okay.
So we did query by car type, but then also a little bit of very rudimentary natural language processing to see which one matched, which one didn't. And we only kept the ones that matched very well, things like that.
Okay.
Okay, so we did that. So now there is an issue. The issue is we have that, this is why subsequently after this project, I got very interested in domain adaptation. So we have like cars, you know, we got a lot of images of cars, and we have cars that look like this. You know, high resolution cars, like right in the front and center in the middle. There's nothing occluding it. There's no trees, whatever. And then on the right, we have, you know, the cars that we're trying to recognize on Google Street View images. They're not very high resolution. They're very blurry. Like one car is in front of the other car, etc. So if you train a classifier on images that look like this and try to test it, classify cars that look like this, it's just not going to work. So you get like, specifically, we got probably like 4% accuracy or something like this, or 5% accuracy. It doesn't work. For us, so what we did was we had no choice. So we had to basically take a subset of our Google Street View images. So these images, a subset of these images, and we had to annotate them. And so we found experts. We found people. I mean, there are people who are crazy. Like there are people who know, imagine I show you this thing and I tell you, what car is this? And there are people who can tell me this. Now, we made a UI, again, like we had to iterate on the types of UIs that we made. But like, so we guide them through the process of annotating this image. But if they don't know, they have to know something, you know, they have to know that, is this I don't even know what this is. It's a Nissan. So yeah, they have to start somewhere. But, you know, also, like, theoretically, you could, I think it's a Nissan, it says Nissan.
I think the taillights look like Nissan stuff.
But like, so, you know, theoretically you could do it if you're not a great car expert, but because we're trying to annotate as many images as possible per time, we test you first with some gold standard. So we first had a gold standard of images, and then we see how fast you can do these images, and then that's when you're allowed to annotate our images.
Oh, wow.
So,
okay.
Right, yeah. So we finally gathered this training data, which I'm still supposed to be releasing. So we have a lot of images, so we split them into training, validation, and tests. So we have a lot of images from Google Street View, and we call the ones that we got from e-commerce sites product shot images. So we have this huge data set of cars, and once we had this huge data set of cars, it was time to train a car classifier. So, you know, remember our goal is to, by the way, at this point, we've spent about almost a year on the project. Once we got to this point, we had spent a year and about $30,000 on this project, I would say, more than a year. Okay, so now we want to, basically we want to detect and classify cars in 200 cities. These are the cities, and in 50 million images, right? So at that time, this was in 2014, I think. I don't remember. Yeah, 2014-ish. So question is, efficiency was like very important because we had 50 million images, which was a lot at the time. So at the time, the state of the art for detection. So detection is the task of localizing an object. So here I say, you know, I put a bounding box on the car. So that's detection. The state of the art at the time was something called RCNN. Nowadays it's let's say mask RCNN or faster RCNN. So they've sped it up like over the years. But at the time, it was RCNN, and it would have taken us 31 GPU years to run RCNN to literally train a car classifier using RCNN. So, but then before that, there was something called DPM, and DPM was pre-deep learning. And at the time we were like, okay, let's see how we do with DPM, because really here we can you know, shave off, like, we don't have to get, you know, 100% state of the art, because like, it's just, efficiency is so important. Like if you know, 31 GPUs is just not going to work. So we used, and then we're like, okay, we'll do the whole pipeline with DPM, and then, you know, and other stuff. And if it doesn't work, then we'll go back and like reevaluate like the different parts of the pipeline. So with DPM, we were able to train a car detector. So basically just something that tells you where a car is. It's not telling you what type of car or whatever, just tell you like where the car is. So we did this in 2 weeks with about 200 CPU cluster. So our task was broken up into 2 tasks, right? So with DPM, we just like, it told us, you know, where there's a car in an image. And then what we did was, once it told us where the car is, we cropped out the place. I mean, I'm simplifying a lot of things, but we cropped out where the car is, and then we just feed it into the most basic convolutional neural network you can imagine, which is AlexNet, which was the very first CNN that won the ImageNet challenge. So that was the CNN that like brought deep learning back on the map, and people were like, whoa, this works, because it was 2012 ImageNet challenge. AlexNet like got, you know, the highest scores on everything by a large margin. So anyway, so this is the most basic CNN. And so once we crop out where the car is, we classify it into one of about 2,600 classes of cars. So now, so that's the architecture of an AlexNet. Anyway, so now we detected about 22 million cars. That's a lot of cars, about 8% of the cars in the US. And we classified them. And so how well do we do? In terms of detection, a lot of times in computer vision, we use average precision. So it's basically like the area under an ROC curve. So our average precision was about 65%. 2600 way accuracy was about 31%. So it's like, you know, classifying at the very fine grained level. And the higher up you go, like, for example, country, like, you know, where is it German or is it American, etc. That was about 84%. Body type is like sedan versus, you know, coupe, that kind of stuff was 78%, etc. So here is, I'll show you a confusion matrix. So the claim I want to make is that our mistakes are reasonable. So because we're going to use this to like do demographic analysis, some kinds of mistakes are much more costly for us than others, right? Like, so if I consistently mistake a really expensive car for a really cheap car, that's not good. But if but here you can see that we mistake like crew cabs for extended cabs, for example, or for regular cabs, and which is pretty reasonable because they're all trucks. And sometimes, you know, you mistake convertibles for coupes, because sometimes you can't even tell whether a car is a convertible or a coupe or from a particular angle. So I feel like, you know, our mistakes are kind of reasonable. Okay, so now, yes.
In the previous one, when you were given this information, did you have different models to classify these, or did you use the same model to classify all this information?
Classify, you mean the cars? Yeah. Oh, you know what? We experimented. So we ended up just like having one model. One model to do the 2657 weight classification, and then just use the metadata from that classification. We didn't train, like, actually, I mean, we didn't end up using the different models that we trained for like make and body type, etc. classification, but we did experiment. I remember experimenting with that.
Gotcha. Cool.
Yeah.
Thanks.
Okay, so now we detected cars. We used, you know, it took us 2 weeks to train a car detector, 2 weeks to train a car classifier, and then 2 weeks to run it across the 50 million images. So now we finally have, you know, detected and classified cars and all the different images that we have. So now let's get to like the fun part. So now we just asked a whole bunch of questions. First question is, how green is each state? So like if I just looked at the average miles per gallon according to my data for each state, and I compared it to EPA data for the CO2 per capita, what does it look like? So on the left here, you have EPA data, which is carbon footprint, and on the right, you have the average miles per gallon. And what's really interesting is here you see, and according to us, that the highest average miles per gallon, Burlington, Vermont has the highest average miles per gallon. And then we saw that Burlington, Vermont is actually the greenest city in the US because it was the first city to have 100% of its power come from renewable energy. So that was cool. That was the very first result that we saw, like telling us that this whole thing wasn't like completely broken, which would have been very sad. And the second thing we did was we were like, can we say something about income segregation? So we were like, okay, let's look at the average car price, according to our data, at each GPS location, and we use this this thing called the Morton's eye statistic. The econ people here might know this, and it's a measure of spatial autocorrelation. So all we need to know here is higher means more segregated, and so we plot these cities. So we see that Chicago is very highly segregated, and we can further visualize this. So you look at the red cars are clusters of statistically significant clusters of expensive cars, and the yellow ones are statistically significant clusters of cheap cars. And then like the creamish color means like there's not really any statistically significant clustering going on. So you can see like if anybody's from Chicago, this is where the rich people live. So I saw like
I live in Chicago and very accurate, I would say.
Okay. And then we also saw, I don't know if anybody's from Jacksonville, but we didn't see that much clustering of cars by like price in Jacksonville. So these were the first, couple of experiments we ran. And here what we did was we just basically looked at one type of car attribute and we tried to like relate it to, a particular type of demographic attribute like income or, CO2 per capita or whatever. But what we wanted to do next is say, okay, let's take all the things we know about the cars that we classified in a particular neighborhood. So let's say a zip code or a precinct if it's for voting, and let's train a model to go from the car attributes that we know to like the various things that we want to predict. So here we represent each zip code as a vector, and each entry in the vector has represents something different. So for example, the number of cars per image, which kind of tells you like the density of cars in a zip code, the average car price in the zip code, the percentage of like, cars of each make. So the percentage of Hondas, the percentage of Toyotas, etc. So this is like, so each zip code is represented as like the attributes of cars that it has. And so then what we did was we used very simple, plain old regression to train a model, going from these these vectors to various things. So the first thing we did was we predicted income. So the data that we got for income and other things that we're going to predict, they came from the American Community Survey. So we have training data for the purple cities. So we used about 12% of our data for training, and so we train on these purple cities and we test on everything else. So here is an example of actual versus predicted values for median household income. And from that one,
how many of the images represented the training set on the community?
How many?
So of the 50 million, what, like 12 million or 8 million?
Well, okay, so what's 12% of 50 million? No, it's so it's not. So at this point, we don't worry about the images because now you worry about the zip codes. So right now, after at this point, every information that you have from the images has been distilled. So right now, our data is all the zip codes I have, and each zip code is represented by the type of car it contains. So now we don't worry about the images anymore because everything, all the information from the images has been distilled into this one vector for each zip code, right? So then the question is like, how many zip codes did we use for training?
Did you experiment with that? I guess 12%, because usually the standard is like 70-30. So to have such low on the 12%, was that just a?
Well, it depends, because I mean the standard depends on what you want to do. So if the point we want to make, so we swept it to C. But if the point we want to make is you can actually use this to predict demographics, and then we tell you, actually, you need 70, you go around and use like, and you have to gather survey-based data for 70% of your cities, and then you can like, use our thing for 30%. No, nobody's going to be that like excited by that. They're like, well, I might as well just like gather survey data for the 30%. You know what I mean?
Sure.
Like cities, right? So, so we did sweep it, but we wanted to show that like actually you can use a little bit of training data.
That's really cool.
Yeah, that was the point we were trying to make.
I think your paper mentioned 15% zip codes, or
is that what I said? Okay, I guess I'm wrong. So between 12 to 15%, right? So the counties that start with A, B, and C, I always get confused. That's how I remember it. We used.
I think it was like 12% of counties. I think it was the postal. It was 12% of I think zip codes, and then maybe 15% of the precincts or something like that.
No,
right?
it's 12% precinct and 15% zip codes.
Oh, okay, gotcha.
There is
someone who knows my paper better than me. That's great.
Yeah.
Yeah. So anyway, so here are some maps. That's basically what we're gonna do from now, between now and like a couple of minutes from now. Actual versus predicted maps, and then you can do like some fun things. You can say like, what are car attributes that are most highly correlated with rich neighborhoods and not so rich neighborhoods, and clearly like it makes sense. It passes the smell test that like that you expect the average car price to be like very highly correlated with wealthy neighborhoods. And we found that foreign cars are also very highly correlated. I had to check all of this market statistics and data just to make sure all this stuff kind of made sense. So then we did the same thing for like voting patterns. And so here you see actual versus predicted values. You see, oh yeah, like here is a map. Like on the left, this is the actual and this is the prediction. But then now I'm showing you another map. Here is actual, and this is just the ratio of sedans to trucks. And I'm trying to tell you something here, but but anyway, so the ratio of sedans to trucks is a very high predictor in our data set, in our particular data set, because our data set is very highly skewed towards cities, of who voted Democrat versus Republican. Here are some more fine-grained maps at the precinct level. And so then here, you can ask the same question. What is most positively correlated with, people who voted Republican versus Democrat? A lot of trucks were very highly, correlated with Republicans. And then, so I feel like this kind of tells you cities. So the percentage of sedans, the number of cars per image, which tells you like a high density of cars were very highly correlated with being Democrat. And also, and then you can ask a question, given that conditioned on the probability that I'm, in a place where I have more sedans than trucks, like what's the probability of someone voting Democrat versus, Republican? And it's pretty high. So we were surprised to see this. Okay, and then we did the same thing for race. Here's an example of Seattle. And we do some fun things here, like what are cars that are very highly correlated with Asians. We found actually a lot of market research says that a lot of Asians buy Asian-made cars. So Toyota, Honda, etc. Same thing we asked with the same question with Black people, Cadillacs. I actually read a whole thing about the history of Cadillacs and African Americans, which is really interesting because I think Cadillac was one of the cars that directly started advertising to African Americans. A lot of car companies wouldn't give loans, wouldn't, you know, would make it very difficult for Black people to buy cars. And I think Cadillac has a history. I cited in my paper the reference for that. And then we can ask the same thing for white people. So like here, you can just like, you know, see if whatever stereotype you had is like, I don't know, corroborated or not. And so then, you know, one last thing we did is we looked at crime. And we asked the same question, like what are attributes that are most highly correlated with crime? And the number of cars per image, that makes sense. Like, you know, you're in a densely populated area, you expect the crime to be higher. The thing I was confused by was like vans, the percentage of vans in a neighborhood. But then again, I was like looking at, you know, what's that show, Breaking Bad, you know, and like had a white Chevrolet van. It was like, oh, okay, you know. So maybe it makes sense. I don't know. You know, these are correlations, so you can't like make any sort of causal associate, you know, thing. You can't say anything causal about them. So anyway, so in the future, what I want to do is I want to look at this over time. So here's an example of New York in 2007. So Google has this thing called time lapse. So you look at New York in 2007, there's Brooklyn and 2014, and like you can see how it's really changed. And you can see the same for the opposite change for Detroit. And I want to know, you know, can we look at this change? Can we analyze it? Can we try to predict census data for if it's available? So we did some initial experiments on that. Here's an example of the percentage of the change in the percentage of high school educated people in New York. And so blue means it's gone up, and red means it's gone down. So here's the actual versus predicted maps. So this is work in progress. So yeah, that's it. Thank you for listening to me. And if you have any questions, I'd be happy to take them.
I had a couple of questions, Timnit.
Sure.
Excellent work. I think it seems to me a pretty very, very detailed piece of work. Your election predictions were made for 2008. Any chance, because whatever I understand, the 2016 elections, you know, had a lot of different results came up. So do you think the results will hold good for the 2016 elections also in terms of the predictions?
I don't think so, because I think that to make this kind of method like accurate to the level where you can predict like swing, you know, states or things that'll change, I think you have to augment it probably with like maybe more publicly available data. I don't know if first of all, if cars by themselves would tell you that data. And I don't know if you can, you know, if just looking at, you know, the cars in Google Street View will tell you that data. So that's something I'm really interested in, but I don't know if just this specific method on its own would do that. But a lot of people, by the way, like, because we submitted this paper right around that time, and people were just like, oh, you should try to predict like the current election. Because we would have to gather more timely images to do that and rerun our pipeline and stuff. And I was like, oh God, I've done too much work already, so I'm not gonna do that. So yeah.
Just a couple of, these cars, is there any data as to how many cars were actually parked and how many were moving cars in the images?
You know, there was no data, and we didn't distinguish between cars that were parked or cars that were moving, or actually sometimes like once in a while the same car would be in front of the Google Street View car, so sometimes you double count it. So it's actually very, very noisy. Like whatever we did, it's pretty noisy. And also even if you think about Google Street View, when they take like images, when they take pictures, it's not really at exactly a specific time. You know, so actually I'm pretty surprised that any of this worked, because it's pretty noisy, right? Like, and some people were telling us that it wasn't going to work.
And the last question, sorry, any distinction in your data between residential areas and non-residential office areas?
No, so that's a good question, because that's actually what I did some experiments looking at DMV data, like Department of Motor Vehicles data, because that tells you cars that are registered to like some person, and that's not what this tells you, right? So what this tells you is different. It's different in that, you know, if I live in a commercial area that has many cars that are parked, or I live in a commercial area that has a freeway around it, then that would come up in this method. It wouldn't really come up if I use DMV data, right? Okay. So we didn't make that distinction, but I think that like some of our features, like the number of cars per image, you know, how densely populated the cars are, et cetera, I think these tell you some things about the type of neighborhood you're living in. Are you living in a neighborhood that has a lot of cars parked on the street? Are you living in a neighborhood that has a lot of that's next to the freeway, et cetera,
Yes. Okay. Thank you.
Mm-hmm.
I have a question.
Sure.
Okay. Can I ask, why did you choose car for this modeling? Like, you could use like the picture of the house. It's give you, I think, some information based on the image, based on the.
So I'll tell you two answers. I'll tell you like the real answer and like the answer I can, you know, tell people, like the answer that, because everybody asks me. So there's some truth to all of them. So when I look at Brooklyn, for example, there are houses there that have been around for like 100 years that have not changed. But I know the demographic has changed, like, you know, and I could say the same thing about Palo Alto. Like, there are houses there where people bought them in the 70s for like $60,000, and they're all of a sudden now $3 million. The house has not changed, right? But, you know, but now I see Teslas there. I see a Honda, you know what I mean? So I think that cars are more dynamic in that way, like in what they tell you. But actually a different, but I'll tell you like another answer also. Another answer is that when we started out this project, our only goal was not to do this demographic analysis. We had multiple goals. One of our goals was to do fine-grained image recognition. And for fine-grained image recognition, so cars are a good case study of fine-grained image recognition, because there's so many different kinds of cars. You know, and like they're occluded, and there's like so many of them everywhere. And so like doing fine-grained image recognition in the wild and gathering a data set to do that, etc., that was also one of our goals as part of this project.
Okay.
Nicholas had a question from in the chat. Any intent to apply this to commercial applications, real estate investing, retail siting, things like that? What do you think about those applications?
There's so many people who are interested in doing that. Like since last year, I was approached by insurance companies, bank companies. There's a company called Mapillary, I think, that is already doing this kind of stuff. There's another startup that's already doing this kind of stuff. There's a whole bunch of investors who approached me, you know, like, I did a startup before. You know, I don't feel like doing a startup right now. I'm like, I want to do research, but I feel like there's a lot of people who are interested in this kind of thing. And what I'm more interested in right now is to apply this to like really to places where it's really hard to get survey-based data, right? Like there are places, my friend was telling me right now, in Zambia, they're having a cholera outbreak, you know, and so can we use publicly available data just to see, you know, how that outbreak might be spreading or something like this? Or, you know, there are places where it's really difficult to get census data. You don't even, you know, at least in the US, we're saying it's hard, but like we have very detailed census data. There are places where it's difficult get that census data, but getting this data would be very, very helpful to find out, what the poverty rates are in different places, etc. That's kind of where I want to take more like the direction I want to take this work.
Mm-hmm.
Yeah.
And then there's a question from Hong. You listed some R values, prediction versus real consensus, but is there a way to have a sense whether the vision-based approach is good enough and how to recognize the bottleneck?
Good enough. I mean, good enough is hard. So what you do is you have a training set, you have a test set, you look at the R values, you look at RMSE is another one, and so you have all of these different metrics, right? And then you look at, what you consider to be good enough. I don't think it's good enough. It's not good enough to definitely, to replace the census or anything like that. But I think it's a promising direction to take it, because there's some stuff that's going on right now, for example, where, the census is really important because of redistricting for politics. And there have been a whole bunch of cases where certain groups of people have been undercounted on purpose. And so, the question is, can you augment some of these survey-based methods with some like publicly available data to like figure out maybe where people are being undercounted and like try to make the census process like more honest. That's the kind of stuff I'm thinking about. But like, I could tell you right now, it's not accurate enough, because also it's hard to figure out outliers with this kind of method, right?
Mm-hmm. Interesting. Well,
can I ask one
thank
question?
you. Sonia wants to sneak in one more question.
Sure.
Based on you choosing the car for the model, did you consider like how many % of people they don't have a car? So
yeah, that's interesting.
In this research.
Yeah. So so
I don't have a car, like so.
Yeah. But you don't have a car, but like the neighborhood, what I'm trying to decide is not about, I'm not trying to say something about you based on the car you drive, right?
I mean the percentage of the people that
right, but I'm trying to say something about you based on the neighborhood that you're in. So is the neighborhood that you're in a place where a lot of people drive cars or not? So let's say the neighborhood you're in doesn't have that many people who drive cars. Then it'll come up in a couple of the features that'll tell me something, right? Like the number of cars per image will be low, for example. But it's really interesting. I was very worried about this actually. So I was like, what about New York? What's going to happen in New York? But it's really weird. Like after I saw it, actually we could see, for example, what the most I guess what happened is that the number of cars per image becomes a signal, and then whatever car you have contributes to the signal that you have is what I saw. So we could see like, some neighborhoods with some really expensive cars. It doesn't mean we probably didn't, detect that many cars, but whatever car we detected, I guess, was expensive or something like this. So yeah, I mean, I haven't done like a systematic analysis on this, but like it was definitely something I was worried about. But it didn't seem to be that big of a problem for this particular project.
Okay, thank you. Great work.
Mm-hmm. Thank you.
Simna, thank you so much. One of the things that is most interesting to me about this paper is, we spent a lot of time kind of thinking about algorithms and, tweaking the algorithm, and, often what gets lost is like the end to end, just the amount of work that has to go in end to end to put together a project like this. And when you dig into this paper, you see, okay, you first had to figure out this piece, and then this piece, and then this piece, and then this piece, and then whoa, 5 years of your life is dedicated to this paper.
Yeah.
And it's really great to see that in perspective, and thanks so much for sharing it with us.
Thank you, guys.
Thank
All
you.
right.
Thank you.
Bye, everyone.
Thank you.
Thank you.
Thank you very
Bye.
much.
Bye.
Thank you. Bye.
Thank you, Sam, also.
Bye-bye.
Yes,
Thank
thanks,
you.
Sam.
All right, you've made it this far, so I'm guessing you like the meetup. In that case, please, please, please give the video a like and smash that subscribe button. And when you're done, head on over to twimlai.com/meetup to sign up for future meetups. Catch you next time.